Hello, Amiga coders. This is Photon again. Welcome back. We're going to continue the Blitter saga, and I want to go over a little bit more about the registers themselves before moving on to scrolling and stuff. So I've prepared a little bit here. You will have to get these from my files or type them in yourselves. And these are the names of the registers that are relevant to using the Blitter. So first of all, we have a strange register up here, and the base register for these is the usual custom chip address, which starts at DFF 000. What that means is that these are offsets to that base address. And I'm going to introduce a way to address these in a more readable way, which also introduces addressing modes a little bit more than for just copper poking. I'll explain that in a bit. I'd like to give you an overview, so let's go through these. Blitter destination data register contains one word, and that is the result of the last blitted word. So the Blitter has combined all its sources and performed its logical operations, shifted, masked, and so on, and the result ends up here. And this register can be read only to check things like if Blitter objects or bobs, that is Blitter generated sprites, for those of you who play games, if they intersect, you can use this for collision detection by anding their outlines in a separate sort of collision bit plane. You can detect these collisions. If they do intersect, there will be bits left in this word. So it's also used for MFM decoding, where you XOR all the words of a sector, and you get a checksum of sorts out, and you can compare this to the actual checksum. Here's the read-only version of DMA control register, and this is only useful for one thing really, namely to check if the Blitter is working or not. This bit will be 1, as we discussed in the previous tutorial, until the operation is done, at which point it becomes 0, and you can safely go on to overwrite the values in the Blitter registers to instruct it for another blit. Here then are the conventional Blitter registers for setting up a blit, and they're pretty much in the order that you need to load them. There will be, I will talk a little bit about how you should think when you load the registers, which order you should load them in, and so on. So this tells the Blitter, it puts the Blitter in a sort of mode. You can set it into area fill mode, line drawing mode, or the conventional combination of sources to form some sort of output. That's still sort of an area mode because we're working in our memory window, or memory rectangle, if you remember the previous tutorial. But it does not perform a fill operation. It just shifts and masks and combines the bitmaps that you point to. So these two control words is what I went through in the previous tutorial, and I will expand on that. Here are the mask bits. The two mask words form two sets of 16 bits masks that will crop the rectangle at the left and right edges so that you can not only blit memory windows that are an even width divisible by 16. So it's a way of adjusting that. You can also use these registers for patterns at the edges, but only at the left and right edges. They simply mask the first and the last word on each row in your blit. Here then are the pointers to the sources and the destination. And finally the blitter size. I will not go through these, as these are, well, very rarely used, I should say. And they're only for special modes and extra large blits. Here are the modulo registers, which we also discussed in the previous tutorial. Discussed, I say, I told you about them, and you didn't have anything to say back to me. But anyway, and finally here are some interesting registers. Instead of pointing the sources A, B, and C to a memory address, where hopefully some graphical data is stored, you can put patterns and fill values and all kinds of things in each of these three words. So these words then will be used as a pattern that repeats for every word of the blit. So it's sort of three constants that you can use in if you have a bright idea for some effect. You might want to I don't know, mask a bunch of stuff in memory, and you want the mask to be dynamic, and then you want to sort of use this pattern as a global constant to mask every single word in the blit, and things like that. And finally, the write-only version of the DMA control register, which partially enables Blitter DMA and has another bit to give Blitter priority over what? Over the CPU, of course. When this, we have blitted so far without knowing the state of this bit, which is fine to keep things simple, but when you optimize your program, you want to control whether, well, if the CPU has a lot to do, you want to set it to 0 to let the blitter give away every fourth of its intended blitter cycles to the CPU. Otherwise, it will hog every available cycle from the CPU until the blit is done. So this is a way of naming these cryptic addresses. I don't use it myself, so I will probably have a little bit of difficulty in remembering the exact names, but I think I'll do fine. So we were here in the init code, and we had experimented by changing the blitter control register value. This is the end result of all the combinations that are possible between the three sources available to Blitter. We're not using any one of them, but still this controls the output then. So if we set all the bits to 1, all the output bits will be 1, and if we set them all to 0, all the output bits will be 0, regardless of how many source channels are enabled, and so on. There are some bits in BlitCon 1 the second control word, that control things like which mode you're in. You can enable area fill mode, and you can enable line drawing modes, several line drawing modes. And you can tell the Blitter to work in descending mode by setting bit 1. And what happens then is that the Blitter reverses completely. Whatever address you pointed to start with, it will start from and then work backwards in memory towards address 0. And any modulo you write, it will subtract instead of add. So it will work backwards and skip backwards. That means that you can, when you start, you must point to the lower right corner, actually the last word of the blit, the lower right corner of your defined memory rectangle, and you must keep the positive value here, Blitter skip, which was 12 or 14 or something, so that it subtracts the modulo after it reaches the left edge on each row. So that's how that works. What say we start by renaming these registers? Well, this introduces an addressing mode. We've already used it down here to specify offsets to an address. In this case, we've loaded a base address into A1, and a few bytes higher up in memory from this address, we've poked our high word and low word like this, and we're going to use the same addressing mode that will work the same way. It will temporarily add a value to the base address register. Whether you prefer, well, which address register should we use? Well, A7 or the stack pointer is used. A6, some like to keep exec base in address register in A6, and put the base address for the custom chip registers in A5, but I figure since we've turned off the system, we no longer need exec base. That means that that register is free, so we can use it instead of permanently, for the whole demo, store a library base address that we'll never use. So how do we do this? Well, we load the effective address of the custom chip registers into A6, provided we type comma instead of an M. And how do we type this to put this value in DMA-con? Remember, there were two registers, a read-only register and the write-only register, and we'll use both of them here. We're going to write a value. That means we're going to use DMA-con without the R for read. And we're going to add A6 within parentheses. I have a function key for that. So this is basically what it does. Let's go down and check again at what address this is. It was at the bottom. It's hex 96. So hex DFF 000 plus hex 96 indeed results in the same address that we replaced. So here we test the DMA-con read-only version, and we can still use the offset notation. And likewise, we can replace that. And what this does is it saves 4 cycles on a 68,000 CPU. And it cleans things up a bit, perhaps, if you're used to this sort of thing. Now, we're testing bit 6 because 14 minus 8 is 6. Why do we do that? Well, because the bit test operation, I wanted to expand on this in the last tutorial, but I forgot. I'm sorry if I confused you. We're going to test bit 14, and bit test is a byte operation, while DMA-con R is a word register. That means that bit 14 will be the bit 6 of the first byte of this word. And we need to point the bit test operation to the direct address, which is hex DFF002. So I don't know if that cleared things up or just confused you more, but since we know this now, we can clean it up, and we can continue cleaning this up, and we're loading this into BlitCon 0 and BlitCon 1, but that's not, whoops, no we're not, we're deleting stuff. I'm going to put the proper, I had descending mode before. I'm going to put the original clear operation we had originally there first, and put it back in there, and write that at BlitCon 0 A6 ding ding. Thank you. Because this address equals hex DFF040, and we write a long word to it, we set both BlitCon 0 and BlitCon 1. And so it is for the high and low words of the pointer address. We can write this to the DPTH. I told you I was no good at these. And it will write both the high and the low word of this address. This then is BLTD mod, and this is the BLT size. So there we go, we've cleaned it up a little bit. The next step then, well, I'll tell you a little bit about the mask registers, because they come into play now that we're going to convert this into a copy instruction, a copy blit, because eventually we want to be scrolling this rectangle, and a scrolling operation is a copy blit with a shift added to it. Suppose we demonstrate the mask registers. What's the best way to do that? Well, suppose we point both the destination and the A source to the same address, and we'll say we copy from the same address to the same address. The only difference is we want to mask the edges, because we don't want to, well, just for demonstration purposes. What to do then is to calculate, we certainly need to enable another source here, and these source and destination bits look like this. Bit 1 here in this nibble is obviously the destination. Obviously I say, because I know it is, which is a poor explanation. But bits 3, 2, 1, and 0 in this nibble correspond to the sources A, B, C, and the destination D. So to enable A and D, we need to make a value that looks like this. And we can find the value of this bit combination by typing like this. Actually, I wanted to clear the screen here. And I didn't get my... to get your previous command back that you typed previously, just press arrow up. If you just press enter, obviously, well, still kept it. Anyway, the value is 9. And that means that we can enable the A source and the D destination. In this, let's call it a source mask, even if it does contain the destination. Channel mask is a more appropriate term for it. So this copies from the A pointer to the D pointer and makes and it's very depressing because it doesn't matter what the A pointer, what the A source points to. Even if it contained data, all the output bits would become 0 with this minterm or logical combination byte here, and these two nibbles. So that's not very useful. We're going to calculate the so-called minterm, and there are various complicated formulas for doing this. I prefer this very simple method. And I'm going to do it down here after the entire source, and I will make this, I will put these constants at the top to make sure that they're set before the assembler encounters our init code. So let's put them there, and let's go down here and create a comment section. If you type end, that tells the assembler to stop assembling and ignore whatever is after this end instruction, this end compiler directive, I should say. So let's type some notes freely here. I am a little cat and I'm a dirty dog. Woof, woof. That's the lyrics of a camp Swedish pop song from the 80s. Anyway, actually I think it goes meow 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 meow, but anyway, let's see if it assembles. Hopefully it does, if we haven't made a boo-boo. And you can see it completely ignores these silly instructions, whereas it says legal operator if we... So that's a parenthesis for now. Here's the way to calculate a what is essentially an 8-bit minterm that we will supply in the Blitter control words. This is just so that you will have the tools to do any blit. As we'll discover, there are a few combinations that come up again and again, and I will explain a bit about those. So let's see. Goodness me. So let's make a little table here. Well, you know what, let's leave those at 0 for now. What I'm typing here is the I'm simply incrementing the possible combinations here. These here are the numbers 0 through 7 counted upwards, and it just so happens that when you type ABC as the column headers here, that means that channel A has the value 4, channel B has the value 2, and channel C has the value 1. You don't have to care about that really. These are just line numbers, and these are just the bit combinations the Blitter uses to combine channels A, B, and C. So what you want to look for is these output bits. So what happens is, let's say that we wanted you type in this column, you change the bits to 1 that you want to be set 1 for every combination of the sources here. That means that if we want to ignore channels B and C, if they can be anything, and the output should be a copy of channel A, you simply copy the bits to the destination, like that. If you wanted to make an OR operation, if you also wanted to include the B channel, when the B channel is 1, then the D channel should be 1 also. Then you would add these bits. And if you want to mask and XOR and so on, you only have to, it's very simple to think about this, according to me, because all you have to do is go through think through all the combinations and set the D bits to 1 where you want them to be 1 and 0 where you want them to be 0. This means you, instead of calculating formulas with capital A's and B's that you can see as an example in the hardware reference manual, and use AND, OR, and XOR and parentheses and so forth to calculate your minterm, you can, I think about it a little more simply. Such as for this copy blit, for example, it was easy to calculate the minterm. It's already calculated. How is it calculated? Well, these 8 bits are the 8 bits we are looking for, and this 1 bit is bit 7 in that control byte, in those 2 control nibbles. How do we calculate this value? Well, we take these bits in reverse order so that we get a binary number, which is 1 1 1 1 0 0 0 0. Who says guys can't multitask, huh? And if we type that out, we get hex F0. So that means we can take these nodes and directly insert them in our copy control word. So that means these 2 nibbles become F0. And that is indeed, 9F0 is indeed a valid copy blit combination. The 9 enables the proper channels, and the F0 combines them in the proper way to make the destination a copy of the sources. If we run this now, we've suddenly changed. We're not quite done yet. We need to also set the A modulo to the same value, because we're using the A source, and if we don't set the A modulo, it could have been set to anything by the operating system or another process, another part of your demo. But if we run this now, it again will be very depressing. Instead of our cleared rectangle, we have just copied the rectangle to itself, basically. And that's no good. So how do we make this interesting? Well, let's introduce the mask registers. I prefer to set both in a long word. You can set them individually if you like. One important fact is that if your blit is only one word wide, only 16 pixels wide, then both words will be ANDed with each other before masking any of the sources. That means that if one of the words is 0, then the resulting mask will be 0. If all the bits are 1 in one mask word and half the bits are 1 in the second mask word, then only half the bits will be set in the combined mask. They're simply ANDed together. Look up the on Wikipedia logical operators and binary and so on, if you need to need a refresher on those. Now, if we set this to, well, we want to put something, since the first word mask is address DFF 044, and we move a long word to it, it will set both the first and last word mask. If we set this to 0, something should happen. I have not rehearsed this, so anything might happen. Well, what we got was some sort of mask on the first word of the rectangle, if you can see it. But it doesn't quite look like it clears the whole word, so what's going on here? Well, because I've made an error. I've actually poked the operating system right now. So I'm going to test if the operating system is still alive and update the source and reset the Amiga. Okay, you didn't see that. Asm cool? Yeah, we're Asm cool, dude. So we're back. We've escaped another bug. What we did was write to address hex 44, very down low in memory, probably overwriting some important vector or other. And we could have just ruined everything. What happened there was that we didn't set the first and last word mask. We poked the wrong address, and therefore it was set to whatever the operating system or some process used for a mask for its last blit. So no wonder. Now we should get to blank edges on the left and right edge of our defined Blitter window. So that's how the mask registers work. If you want to make some fancy mask, let's say that you want to mask away all the, let's think here now. Well, let's say you want to mask away every other pixel. You can put this in, and you can see that it indeed clears vertical 1 pixel columns at the left and right edges of our rectangle there. So that's it. I want to tell you a little bit about the loading order of these registers. And the working operation of the Blitter. when you're using these shifts and masks, naturally, if you want to set that to set all the bits, not mask anything, you do it like that. We didn't have to set the mask register before we had a copy blit because we had programmed it to set all the bits to a definite value for all the combinations and blitter operations. Now we do, and if we set all the bits to 1, we have a normal copy blit again. Now, what happens if we shift this? Well, let's try it. Of course, there's no use in setting the B source shift register. Nothing will happen because the B source is disabled. Only the A and D source, A and D channels are enabled. So, however, if we shift this, we should see some difference at least, and we do. So that's basically how you shift things with the blitter on the Amiga. I will leave scrolling for the next tutorial, but I would like to go through the order of operation of the blitter and the order of loading the blitter registers, because it can cause you bugs sometimes, and then it's good to know. When the blitter performs its operation, it first masks, then shifts, and then combine the sources logically. That means, normally this means that as long as you, normally this means that you want to set them first. And this is a bit of an bit overkill, but you may want to use the blitter data registers, these ones, at one point, and then you must decide whether you want to set them before shifting and masking or after, because when you write, these ones, because when you load them, and if memory serves, it will be latched immediately, so that they will already be available at the start of the blit, and that means that if you shift and mask them afterwards, they will indeed be shifted. That is if you set the mask and shift addresses. And now I've confused you a little bit, because I talked about the operation of the blitter, masking, shifting, and logical combination of sources. That's the pipelined operation of the blitter once a blit is in progress. This is different, but normally you will want to set up the blitter control registers and the mask first, and the pointers and modulos at any point, really. And finally, of course, the blitter size, because that's what triggers, writing to this register triggers the blit. It's also important to tell you that none of these registers, except for, of course, blitter size, because it triggers a blit, need to be set. Basically, you could have a blitter loop that consists of a blitter weight and a write to blitter size. These registers will contain their values between blits, and so if you're doing many blits, one after another, such as, for example, coding some cheesy Bob record or some crap like that, then you will only need to set these ones up once. And the exception are the pointer registers. When a blit is finished, when this blit is finished here, then the blitter channel pointers will point to the word after the last word processed, and that includes modulo. That means that naturally when you blit a memory rectangle like this, you skip to the next row, and this is true also after the blit has finished executing. During the blit, these pointer register will be increased or decreased according to the mode of the blitter, this flag, and it will add modulos for each row, and after the last row it will finish up by adding the modulos, so that you can basically chain blits. And this can be useful if you have a really big blit that you want to split up, or you want to split it up into small blits because you need to do something with the CPU, or in the case of a line drawing mode, that you want to draw a line and then continue drawing another line, for example in a polygon, so that if you draw a triangle, you just draw the first line and then just set the end point of the next line, and so on. That doesn't mean that you can move all these up here before the wait blit. If you initialize blitter registers, you must always precede it with a blitter wait like this. So this would be a valid way of doing it if it weren't for the label conflict here. And finally then, we will clean up a little bit more. By putting this in a little nice subroutine with a word of warning. Excuse me, that was not the word of warning that comes now, namely that calling a subroutine, of course, incurs a performance penalty. Of something like, I think it's 28 plus 36 cycles, which can be hefty if you're doing a lot of blitz. We don't. We do only one blit, so. Finally then, the blitter nasty bit. Oh yeah, let's get blitter nasty. What it does is give the blitter absolute priority over the CPU. And that means that the CPU cannot perform any work while the blit is in progress. An exception to this is that you can squeeze, if you're lucky, you can squeeze in there's something called prefetch in the Motorola 68000 CPU, so that you can so that this instruction, well, it will actually not be executed before the blit is started. When you trigger the blit, there's room for a small instruction, small as in memory access and total instruction size. You can squeeze that in here and get it calculated before the trigger of the blitter takes. So that's a good thing to remember for performance. And to set the blitter nasty, we set bit 10, just verifying so I don't lie to you. And let's check what that is. Bit 10 is oops. Is hex 400, which means that we can... What the hell did my bookmark take? No, apparently not. We can set it here, and this will then ensure that the blit is executed in the shortest time possible. So I think that sums it up for now. We remove the shift. Let's put it back in. And another final note on shifts. You can see there's a disturbance in the force within our rectangle there. A final note on setting up the blitter then is that in ascending mode, the normal mode of the blitter, all shifts are performed to the right. We can show this by moving it a few pixels more. As you can see, it's shifted to the right there. Whereas in descending mode, which I won't demonstrate in this tutorial, the words are shifted to the left. We'll get back to this shifting in the next tutorial, which will feature the scrolling effect. We will then move this one time only blit into the main loop and basically see what happens. See you then.